I session in the morning. Where everyone learns these cookies individually, they individually.
We gotta go to lunch in the morning. Do all that and then how this are those days.
Yeah.
So then like, I know it helps us. Working up.
It's gonna be fun. He's finding us. Giving me.
Hey guys, let me talk about the new calendar that you just picked up.
It's real, it's gotta be.
Okay, so today I want us to do review the handout, the quiz review that you guys did on Friday. I'll go through each problem and just go through each of the types that you're going to see, and then but I do want to do some a little bit of starting the test review, which will be curve sketching. So I want to talk about curve sketching from a log perspective. Tomorrow I'll have a help session in the morning, probably like 9 o'clock on Teams. You don't have to join. I don't have any assignments for you tomorrow, guys. But quite a few of you have some homework that you haven't shown me, so maybe tomorrow can be your catch-up day to get your homeworks in. I do have to, yeah. I'll try to. I know that grades are due, I think Friday, so I'm going to update the chapter 3 homework grades in your in Infinite Campus.
Are we gonna get our quizzes back on Wednesday?
Yeah, a test. Yeah, I'm gonna try to get back to you on Wednesday. But yeah, if not Wednesday, then Thursday or Friday. Yeah. So sorry, it's taking a little bit longer to get that in. But yeah. So I pushed some of the days around here. So on Wednesday, we'll do a check-in quiz. It'll look very similar to your 5.4, 5.5 review that you guys did last Friday. There should be 5 problems, just going through applying those rules, and also product rule and power rule involved. Okay, so we'll and I'll have a morning help session on Wednesday. But tomorrow during my help session, I can also go over any problems that you guys have. But we can also spend the rest of the day, rest of the period to do chapter 5 test review. Sorry, all this should be chapter 5, not chapter 3. And then Thursday, we'll do a full chapter 5 review day. Friday initially was going to be a chapter 5 test, but I'm going to push it to next Tuesday. I'm going to push it to next Tuesday, but I don't want to lose any instruction days because we still have to get through all the log unit. Sorry, a trig unit. So we'll do trig, we'll intro with trig, but then use the second half of the class to do test review. We do trig derivatives on Monday, but then also use part of Monday to do test review. And your test will be on Tuesday. Any questions with I do want to point out a couple of things from the test review packet, even though I think we're only going to do a certain page from here. It goes to the very back. Okay, this is what we're working towards in terms of what we want to be able to do, be able to learn how to do on the very back of your packet, page 36. These are your logs, exponential. These are topics. Okay. Being able to do curve sketching, find relative max, relative min, first derivative test for concavity, all that, everything that you did with polynomials and rational functions, but now from an exponential and logs perspective. So we will do a full practice of this today. Particle motion problem, moving left, moving right, but then from an exponential function perspective. So we need to be able to do this, but all the concepts are the same from what we did with the chapter 2 test. It's just a different set of derivative rules, but the concepts are the same. Finding derivatives involving log, expanding log terms, which you're going to see on the quiz. Logs and exponentials of base A and base E, you're going to see that on the quiz. Involving quotient chain product rule, you'll see that on the quiz. Finding tangent line equation, okay. And then we recently did implicit differentiation, so that will be on the test. It won't be on the quiz. Log differentiation is where you take the log of both sides so that you can use log properties to expand everything and then solve for dy dx. And then find the derivative of inverse at a point. Most of us found this to be, I think most of us did okay with this, where you have to go through that table, right? And you understand that your order pairs are different with your inverse functions, but your derivative is going to be reciprocals of each other. So that will be on the test as well. So that's what we're working towards. I think everything from 3 and down, these are ones that we've seen and we're just kind of getting more exposure and practice with. But then 1 and 2, these are the two big kind of free response portions that we're going to kind of work towards. But I want to kind of give us a little bit more spacing. So our test is going to be next Tuesday. All right, so let's look at page, I'm sorry, your previous packet. Let me go through page 23 and 24 real quick. See if you guys have any questions. I want to run through these problems. So I'm going to go through the solution key here. Oh, did you guys find my mistake here? Did you guys get this to be 8x cubed? Sorry about that. Yeah. All right, so let me kind of go through each of the problems and see if I can help answer any questions. So the first thing we do is whenever you see a natural log or a log expression and you're asked to find the derivative, the first thing you're going to do is you're going to try to expand, right? So if I have some log properties available to me, I always want to take advantage of them. Otherwise, my u value is just too messy and prefer not to do the derivative when your problem is that messy. So this is a above and b below. So natural log of a minus natural log of b right here. And we can either note our exponents or convert our radicals to be exponents, bring those exponents down as coefficients. And now you have a relatively easy derivative rule for natural log, because now we can just do u prime over u for each of these terms, right? So there's my u value. My u value is everything inside the parentheses. So u prime over u, keep the coefficient. U prime over u, keep the coefficient. No need to find a common denominator. Okay, there's our derivative. Number 2, it's a messy log problem, but we can still expand logs the same way that we do natural log. Okay, so log of a over b can be expanded into log of a minus log of b. But first thing is that exponent is kind of over everything. So I'm going to bring the exponent down first and then split up the exponents. So split up my numerator and denominator. Right, so here you see how my exponent is it's just a radical is within the numerator and denominator, but this is over the entire thing. So I brought the exponent down first and then expanded my numerator and denominator. But I just made sure to distribute that 3 through both of my terms. And this is basically u prime over u, but then there's a bit of a change of base that needs to occur. So I need to do u prime over u with a little bit of an adjustment. So 1 over natural log of 3. Okay, since 3 is my base. Okay, so my derivative, all right, keep the 3. That's my coefficient. Log base 3, that's a conversion. So 1 over natural log of 3. And then u prime over u based off of my my u value there. Second term, keep 3, 1 over natural log of 3, and then u prime over u. So really, we're just following what the derivative rules are, right? So I feel like these are pretty straightforward. We don't really have to be creative with the way that we solve these problems. We're just kind of, in a way, kind of blindly following these rules and just applying them. Yeah. Oh, this 5 over x here.
No, the other one.
Oh, sorry, my bad. My bad. That should be 3 over ln 3. Right, that's what you got, right? Yeah, sorry about that. All right, number 3, we need to recognize that before we do any of these rules, that those are two distinct expressions that are being multiplied. So we have to go through what? Product rule, right? Those are being multiplied. So I got to do f prime g plus f g prime. Now, when I reach g prime, that's the e to the u rule, right? And my e to the u rule is e to the u times u prime. So that e to the 2 minus x squared becomes e to the 2 minus x squared times negative 2x. You can leave your answer like this. I took out a GCF and I cleaned it up a little bit, but this is fine. Number 4, it's not natural log, but it's still a log expression. We can still expand, right? Log of A minus log of B. Bring the exponents down in front. And I'm just going to apply my derivative rule, right? So my derivative rule is just u prime over u with a little bit of a conversion that has to occur, 1 over natural log of 5. Here, the second term, I keep the 1/2, 1 over natural log of 5, and then u prime over u. Number 5. I'm also identifying the need for product rule here. So f prime g plus f g prime. But this 8 to the x minus 3x squared, this is an a to the u rule. That's an exponential function, base 8. So the derivative will just be natural log of 8 times 8 to the x minus 3x squared times 1 minus 6x. And so we identify the need for product rule. So here's my f and there's my g. And I go f prime times g plus f g prime. This second term does not give us a visual base, but we have to understand this is what base what? 10, right? So you may want to rewrite that problem with base 10. And also I brought that exponent down in front as 3 so that when I find the derivative, it just feels a lot easier because that 3 is already brought down. So the 3 stays 1 over natural log of 10 and then u prime over u. Okay, so any questions? This is what your quiz will look like on Wednesday. I'll have a morning review, and tomorrow I can also go over any problems during the help session. I'll probably have it at 9 o'clock in the morning, but you don't have to join. You can join if you want, but I'll also record it. Okay, so no assignments tomorrow except for the fact that if you can start test review, that's great. Or if you can, some of you guys haven't shown me homework in a while, so you can use that time to make up your homework. Yeah. Yeah, that's fine. You don't have to clean it up like I did here. This is fine. Yeah. Okay. But a big part of Wednesday is being able to memorize these rules. So I want to kind of have a chance for us to kind of try doing a mock practice, see if we can just recall these rules. So this is how I go about memorizing them. Natural log of u and e to the u, these are kind of parent functions. We should know these. We've used these enough. Hopefully these are not, you don't find these difficult to memorize. They call e to the u, or a lot of people consider this as the quote unquote easiest derivative rule, because the derivative is just the function itself, and then you got to do a little bit of extra with that exponent's derivative. But in a sense, it's easier than power rule because you don't have to do any operations except just to deal with that u prime and keep the original function. Okay. So if we think of this as our parent rules, then log base a is the same thing, but I just need to worry about my conversion with that base a, so I need that 1 over natural log of a. A to the u is similar to e to the u, except it's not base e, it's base a, and base a could be base 2, could be base 3, could be base 8, could be base 9. I do a little bit of conversion in the front, natural log of a times the original functions, and then times the exponent's derivative, right? So it's very same setup as e to the u. Okay. I think one thing that throws students off is where to put that natural log of A. It's like, is it in the numerator or is it denominator? Sometimes students get those mixed up, right? And they pick the wrong one. So the way I remember it is I look at my parent derivative, right? So my parent derivative here, u prime over u versus a to the u times u prime. If I see a denominator portion of my derivative, that helps me remember that there is a natural log of a in the denominator as well. Okay. Here, there's no denominator u, so that helps me remember that my natural log of a goes in the numerator. So that helps me remember between those two. Okay. So why don't we try this? If you guys can just on any space that you have on your sheets or on page 23 or 24, go ahead and write these rules down and see if you can recall what the derivative is. Okay, so let's just see where we are, where we are. And hopefully by Wednesday we can get all these rules, get these rules memorized. We have natural log of u, log base a of u. These are very similar. E to the u and a to the u, these are similar. So I have to get these two rules going before I jump into these rules. Okay, so hopefully we all know natural log of u and e to the u, right? Natural log of u is just u prime over u. E to the u is just e to the u times u prime. Right. It's understandable that we find these more difficult, but why don't we, instead of thinking of it as a brand new rule, why don't we just think of it as just an extension of the rules that we have? So log base a of u also has a u prime over u. But there's something that has to be in front. And what's that thing that has to be in front? 1 over natural log of a. I see a denominator in my derivative, so that helps me remember that natural log of a is going to have to live in the denominator as well. A to the u, very similar to e to the u. You see how this is the original function times the exponent's derivative? I'm going to do that as well. Original function times the exponent's derivative. But this is not base e, it's base a. There's also a little bit of something extra when these go in front here. Natural log of a. Yeah, there's no denominator here, so that helps me remember the natural log of a lives up top. This one here, natural log of a lives at the top. So if we can build it that way, then it doesn't feel like a brand new rule. It just feels like an extension from the rules that you already hopefully know. Hopefully that helps. Hopefully that helps you get a little closer to fully memorizing, and you have tomorrow and Wednesday morning to get this, to get these 4 rules down.
Sure, yeah. Can you show your paper up on the screen again?
Oh, we're talking about like
Your
just
rule, yeah.
my rule here. Yeah. So So these are the same. I just wrote this log base E of U as showing that that's really the long way of writing a natural log of U. I want to keep reminding us that natural log ln is just it's an abbreviated version of writing log base E. So whenever you see natural log, you can always write it as log base E, so you can help remind yourself that you're dealing with base E. Okay, so I want us to do curve sketching from a log perspective today. So if you guys can turn to page 5 in your new packet. At the end of class, when you come get your phone, I have the 5.4, 5.5 morning quiz review printed out. So if you want to pick this up and work on it tomorrow before Wednesday, that's fine. Or you can pick it up and wait for me to go through it Wednesday morning with you. Okay, so curve sketching. We're going to go through a similar process that we've done from our unit 2, or sorry, unit 3 with curve sketching, but now we're looking at it from a log perspective. Okay. So okay, so we're going to find domain first. Domain is just by looking at the function's denominator to see are there any breaks that we need to exclude from our domain. And then we're going to go to the derivative, go through our first derivative sign line, find our critical points, populate our sign line, test each interval, decide whether each interval is positive or negative, and then from there we know is there a relative max or relative min. To find points of inflection, we're going to find the second derivative function, clean that up, find the critical points, populate second derivative sign line, test each interval, determine if there's a change in concavity. If there is, then could be a point of inflection there. And then parts D, E, and F is just helping to sketch our graph. And if we don't finish today, we can always pick some of this up on Wednesday after our quiz. So the first thing is looking at this denominator, knowing that there is something that we got to worry about with that natural log of x, and also just natural log of x has its own domain, so that is going to influence the domain of this function. So as a reminder, let's just kind of step to the side and kind of explore natural log of x and understand what the graph looks like, and a lot of times that can kind of help us determine some values. Okay, so natural log of x looks like this. There are 2 points that it's going to go through that are easy for us to identify. 1, 0 and E1. We know natural log of 1 is 0. We know natural log of E is 1, and a lot of that can help us figure some things out. Now, look at the domain of natural log, right? Just natural log itself, what is the domain? From where? What's the furthest left the graph goes? 0 to infinity, right? So we know that because there's a natural log here, that's automatically going to be a restriction, right? There's not going to be any negative numbers that we can have here. So we already know that the domain is already natural log, is already from 0 to infinity. But here's additional thing here is denominator cannot be equal to what? 0, right? So is there an x value that causes natural log to be 0? 1. So that means natural log of 1 is also an issue because that causes the denominator to be 0. So we have two restrictions, right? One restriction is no negative numbers, and it can't be 1. So if I merge those together, my domain is 0 to 1, and then from 1 to infinity. So this is another way of saying all real numbers except negative numbers and 1, right? Because 1, normally natural log of 1 is fine, but because it's in the denominator, that is causing our function to produce a vertical asymptote. Okay, so now I want to move into finding relative max, relative min. To do that, I have to first find the derivative, right? So let's go to our first derivative test, f prime g plus fg prime. Numerator is my f function, denominator is my g function. So here's my derivative. All right, so let's go through this step by step, right? What's f prime? Times the g function. Back to f. X, right? And what's g prime? Natural log of x becomes what? 1 over x. All over, right, natural log of x quantity squared. This is different than just saying natural log of x squared. Okay, so I want to make sure that we understand this is not the same thing as if I just put natural log of x squared. This I can expand, but this I can't. Okay, so this is the entire function squared, not just the x being squared. All right, let's do some cleanup here. Natural log of x minus 1. I'm going to box this off because this is where I'm going to start looking for information. Okay, how can I find my critical points? Where do I look? Numerator and denominator. Now, remember, we also look for denominator of the derivative as for critical points because it may be a vertical asymptote, but we still want to include asymptotes on our sign line because they help separate our intervals of increase and decrease. All right, so we'll set the numerator equal to 0. We'll set the denominator equal to 0. Right, so I'll say natural log of x is equal to 1. And natural log of what value is equal to 1? E, okay. So it's nice having this if you know what the graph looks like, but I also want to show you that there's another way to solve this algebraically. We know that if I'm trying to solve for x, but it's stuck inside natural log, I can involve what? Yeah, I know that E and natural log, they're things work out in terms of cleaning up between them. So if I involve E with natural log, that works out nicely here because inverse function, what's going to happen here? Cancels out. I'm just left with x equals e to the first power, which is x equals e. So that's a critical point. We can set that off to the side. Here I can take the square root of both sides. Natural log of what is equal to 0? 1, right? But if you didn't know that, you can also work this out by hand. Raise both sides with e as the base. E and natural log goes away. That x will drop down. X equals e to the 0. Anything to the 0 power is what? 1. So I have my two critical points, 1 and e. So I'm going to create my slope, my derivative sign line. Now there's actually a starting point for my sign line. Where's that starting point? 0, right? Because that is the edge of my domain. So it kind of helps me create some boundaries here. So I have 0, 1, and e. Again, e is a a rational number. It's somewhere between 2 and 3. It's around 2.7. Okay, so now I'm going to test my derivative sign line against my derivative function, and I want to choose values that are as easy as I can make it. So what would you choose between 0 and 1? What can I choose between 1 and e? 2 works, yeah. And what can I choose to the right of e? 3. Now 3 is perfectly fine, but I wanna give you another option. Another option is, well, I know e works out so nicely with natural log, right? They have a nice clean way of working together. So what if I find a number in terms of e? Yeah, that's what I would do. I would do e squared. I know e squared is definitely larger than e. It's maybe a little larger than 3, but it's okay. Anything, typically we say choose a number closest, but in this case, e squared is gonna do a much easier job for us rather than interpreting what natural log of 3 is equal to. So one piece at a time, I'm going to insert into my derivative function. I'm going to insert 1/2 in for x, natural log of 1/2. Natural log of 1/2. What's the value of natural log of 1/2? It's somewhere in the negative, right? So like negative 1/2 maybe. So negative 1/2 minus 1 is still negative. Negative over anything squared. Anything squared is positive. So negative or positive is negative. So I know my graph is decreasing. Next up, I plug 2 in for x, natural log of x. Natural log of 2. Natural log of 2, you may not know that value, but if I just try to pinpoint that on the graph, it's positive, but it's somewhere between what? 0 and 1, because 2 is here, right? So natural log of 2 is maybe like 0.5 or 0.6. So imagine 0.5 or 0.6 minus 1. Yes, question?
Since we know e is like 2.7, can't we just plug in?
Yes, we could. And 3 perfectly works fine. I like e squared, and I'll show both ways. And if you want to choose one over the other, that's fine. So if I plug 2 in, natural log of 2 is like 0.5. 0.5 minus 1 is negative. Negative over a positive is negative. So my graph is still decreasing. Okay, I'll do both of, I'll do this last interval with e squared as well as with 3. You can kind of pick and choose which one you want to do. But if I do e squared, this is what's nice about it. If I have natural log of e squared minus 1 over natural log of e quantity squared, what does this clean up to be? I can bring that 2 down, right? And 2 natural log of e just becomes what? Just 2. 2 minus 1 over natural log of e squared. I know that's just positive over a positive. So I know my graph is going to be rising. That's a nice thing with e squared, but we can also do with 3. That works fine as well. Natural log of 3 minus 1 over natural log of 3 quantity squared. Natural log of 3, natural log of 3 is somewhere over here. It's a little bit larger than 1, so maybe 1.2. That's fine. 1.2 minus 1 is positive. Positive over positive is positive. So that works the same way. It's nice having some options. Now, based off my sign line here, is there a relative extrema? Okay. There's a what at E? Relative min. Okay, so we know there's a relative min at E because F prime changes from negative to positive. Now, if I want to find my order pair and I know my X value, how can I find my Y value? Back into the original, right? So E over natural log of E, what does that reduce to be? Natural log of E is just what? 1. So E over 1 is just E. So E comma E, that's the order pair. Okay, F double prime is a little messier. Let's see how far we can get. All right, so there's my first derivative. I'm going to go through quotient rule and what? A little bit of chain. Yeah. Okay, F prime. times the g function. Back to f. G prime outside times inside's derivative. Okay, what's outside's derivative? 2 parentheses to the first power times u prime over u. What's natural log of x become? Just what? 1 over x. Now, denominator is already squared, so what do you think g squared is going to be? Natural log of x squared squared, so that becomes what? Natural log of x to the 4th. All right, this looks like a big mess, but we do need to clean this up a little bit. Otherwise, we're not going to be able to find the critical points. So look at what we can do here. Look at the numerator here. These are 2 separate terms. Okay. Now, what do you notice about these 2 separate terms that could make things easier for us? We can do what? Look for what? Yep, we can look for common factors here, right? So 1 over x, what else do they share? ln of x. So imagine us just pulling or dividing those out. It'll make things a lot cleaner, a lot faster for us. So I'm going to take out a 1 over x and natural log of x. And let's figure out the leftovers here. So if I take out a 1 over x and natural log of x, what am I left with? Just, yep, good. Minus, okay, if I take out natural log of x and 1 over x from my second expression, I'm left with 2. Yeah, good. And you could distribute through or wait to distribute all over natural log of x to the 4th. Now, things are cleaning up a little bit here. Do you see anything that we can reduce? Yep, you see this is nicely factored out. There's no addition and subtraction attached to it. This is fair game. We can take one of these out. Okay. Now, what's inside the parentheses here? I'm going to just distribute, see if I can combine some like terms. And this 1 over x is really just a fractional value in front. If I push it out in front, that x can just drop down and share that same space. So here's my second derivative. Okay. Natural log of x minus 2 natural log of x, that becomes negative natural log of x. I like the first term to be positive if possible. Minus, sorry, 2 minus natural log of x all over x natural log of x cubed. So I just made that x kind of just drop down here, right? So there's my second derivative function. Where do I look for critical points? And denominator, yep. So I set the numerator equal to 0. This one is not as easy to find on the graph, but it's okay. I know I can involve e to clean that up nicely. So x equals e squared. And if I set both of these equal to 0, I'm going to get 0 and 1, very similar to what I had before. So here's my second derivative sign line. I'll have 0, I have 1, I have e squared. So let's pick out some easy numbers for us to plug into the second derivative to determine concavity. So here I'll choose 1/2. Now, what do you think is something that we can use that's easy between 1 and e squared? E, yeah. What can I use to the right of e squared? E cubed, right? So it's so nice because we know natural log and e are just going to work very seamlessly with each other to get something easy for us to apply. So if I plug 1/2 in here, 2 minus natural log of 1/2, that's 2 minus a negative number. So negative over a negative is going to be positive. Sorry, positive over a negative is going to be negative. So this is going to be concave down. If I plug e in here, positive over a positive is positive. If I plug e cubed in here, I'll get 2 minus 3. That's negative over positive is negative. Now 1, there's an asymptote, so I can ignore that, but there is a what at e squared? POI, yeah. So I can plug e squared back into the original function, and I'll get e squared over 2, and that's my DOI, okay? And we'll pick this up on Wednesday. We'll do a little bit of quiz review, take our quiz, and then we'll finish this up and do some more test review, okay? All right, come up and get your phones.